Yeah, good evening, everyone. So, I'm Harish. I'm a PhD student at ISER Mohali, and I will be taking your doubt session come revision sessions for this Algebra second course. So, as we did in the last week, we will be revising the second week's lecture notes first, and then we'll be solving some sample problems. So, as you all know that still the assignment date is due, so we can't solve the assignments right now, but what I'm planning that maybe in the next week discussion session we will solve both the assignment first and second, and uh, this week we will continue as before, that we will be just looking at the lecture notes once again, just a revision of it, and then will be solving some sample problems. So I hope it's okay with everyone. So my voice is audible and the screen is visible, right? Can anyone just
Yes, yes.
okay,
Yeah, it's fine.
okay, that's good. So I hope you are able to see this screen. Let's. So you are so which screen is visible? The white page, right?
Yes.
Okay. So let me just start with revising
ஆ? புரியல.
some disturbance.
நான் அங்கிட்டு போய் இறங்கிடுவேன்.
So Tanya is asking whether assignment problem will be solved or not. So yes, Tanya, we will be solving it, but after the due date is over. Okay. So due date is tomorrow. So once the due date is over, we will be solving it. Okay. There was some disturbance. Let me mute that person. So what we did in the first week, we just uh, understand the definition of what is called a field extension, and then also the numbers that are constructible. And now the second week starts by looking at the examples of numbers that can't be constructed. So by a number that is constructed, I mean uh, a number which you can construct using uh, compass and straight edge. So let me just write down something so that it becomes clear to you guys. So let's say we are on a real plane. So we have a point P with coordinates x comma y, and so this is the x coordinate of it, and this is the y coordinate of it. So if we can construct an angle theta such that the uh, vector joining this origin to this point P forms an angle theta with the x-axis, that means we can construct this point also, right? So x will be your this length, whatever this. Let's say that it's of unit length. So let's say this is of unit length. So this will be nothing but cos theta, and this is nothing but sine theta. So uh, if P is constructible, P is constructible, Then uh, cos theta and sin theta are constructible, right? You can just take the x coordinate and the y coordinate, and the converse is also true, right? If you can construct cos theta and sin theta, that means you can construct the p, because you can take the x length to be cos theta and y length to be sin theta. So this is from week 1. So the week 2 starts by arguing that not all numbers can be constructed. Okay, so lecture 1 of week 2. So it gives those numbers that cannot be constructed. So uh, it gives examples of angles, maybe, that uh, cannot be constructed. So by construction, I mean the construction using straight edge and compass. And we already saw in the first week that there is a very nice theory of such numbers and analogously for angles. So what example uh, was given is, the example was pi by 9 is not constructible. It's not constructible. So this also implies that in general, we cannot trisect an angle. Trisect an angle using straight edge and compass. Why is it so? Because uh, pi by 3 is constructible using straight edge and compass, and pi by 9 is just 1 by third of it, so it cannot be constructible. That means that in general, if an angle is constructible, then it's not necessary that 1 by third of that angle is also constructible. So you cannot always trisect an angle. You can trisect it if your angle is equal to pi. You can get pi by 3, but if you start with pi by 3, you will never get pi by 9 using straight edge and compass. So pi by 9 is not constructible. And what was the idea behind it? So I won't explain the entire detail, but I will just give the glimpse of the idea used. So proof uses let A be your uh, cos pi by 9. So pi by 9 is constructible, means you can uh, have the cos part of it and you can have the sine part. But and the converse is also true. If you have the cos and sine values, then you can say that that angle is constructible. So we will show that there is a problem in constructing this number a equal to cos pi by 9, and how we will do that. So if a is cos pi by 9, then as we want to argue using pi by 3, so what we will do, we will use the identity of cos 3 theta. So cos 3 theta is 4 cos cube theta minus 3 cos theta. Okay. So what does this imply? This is cos maybe for theta equal to uh, pi by 9. What we will get? We get cos pi by 3 is equal to 4 cos cube pi by 3 minus 3 cos pi by 3. Okay. So see cos pi by 3, sorry, it should be pi by 9 here. We're taking theta to be pi by 9. Yeah. So we have already taken cos pi by 9 to be a. So this implies that uh, cos pi by 3, cos pi by 3 is cos 60, which is 1 by 2. So this is 1 by 2 is equal to 4a cube minus 3a. And this implies that you have 8a cube minus 6a minus 1 is equal to 0, right? And this implies that a satisfies 8x cube minus 6x minus 1, right? Now, in the lecture notes, it is being shown that this polynomial 8x cube minus 6x minus 1 is irreducible over q, right? So this is being shown in lecture notes. So this is irreducible. That means it implies that a satisfies this polynomial and it's irreducible. So that means q over, sorry, so the field q of a over q as dt 3, right? Because it is going to be the minimal polynomial satisfied by this, and thus uh, it's the degree of the extension should be equal to 3. And uh, this contradicts the fact that a is constructible. Okay, so because if for any constructible number a belongs to C, q of maybe just let me just change the notation because we are already using a here. So for any b belongs to C, q of b over q has to be a power of q uh, is a power of 2. Therefore, a is not constructible over, because here we are getting q of a over a is 3, which is not a power of 2, so a is not constructible. Okay. So is it clear why a is not constructible? So since a is not constructible, we will say that the angle pi by 3 is pi by 9 is not constructible. This implies pi by 9 is not constructible. So there are numbers which are not constructible. So it's an example of that, and that that was the only thing discussed in lecture 1 of uh, week 2. Okay. So in second lecture, is there any doubt in this? If not, then I will quickly say the important part in the lecture 2. So lecture 2 is symbolic uh, adjunction of roots, and what does it means? So in general, if the f is a field, then and p is any polynomial in f, then it may or may not contain the roots of that polynomial. So what is the idea? We start with a polynomial in the field, and if it does not contain a root of that polynomial, then we adjoin that root with with that field and generate a field extension of that f, and so on. We would be adjoining roots, and then will reach to a field which contain all the roots of that given polynomial. So the idea is, let uh, so just let f be a field and pt be the polynomial in f. Then um, pt may or may not uh, have all roots in f. So what is the idea? So we will try to find a field E which contains f such that all roots of this pt lie in E. So how we will be achieving it? So what you are doing? So let someone just scroll it. I don't know why. Please don't do it again. Yes. So let phi be the map from ft to ft modulo pt. Okay. So you define this map such that t is mapping to alpha. Okay. Then what is p of alpha? Then p of alpha is nothing but the image of pt, right? And since pt is a zero polynomial in this ring, so p of alpha will be 0. So this means phi of p of t is 0, and therefore alpha is a root of pt. Okay. So the theorem says that this is going to happen always. They, this may or might not be a field, but theorem says that there always exists a field such that you have all the roots of the polynomial in the original field in that extension of that in the new extension. So the theorem is, let f be a field and ft belongs to this capital F of t, uh, be any polynomial, then there exists a field extension E of F such that uh, ft is a product of linear factors in ET. So in F, it in this field F, this polynomial small f of t may not be factorizable in linear factors, because the what do you mean? What we mean by factorizing linear factors, that you can write it as some x minus a1, x minus a2, and so on. That means those ai's are the roots of the polynomial, and it lies inside the field. But in this original field, capital F, all roots of the polynomial small f may not be lying. So, but this theorem says that there always exists an extension such that the f factorizes as linear factors. Means all roots of this polynomial small f are inside the field capital E. So, product of linear factors in E or T. So it may not be a product of linear factors in f of t, but there always exists an extension of f such that it can be linearly factorized in that field. So the things will become more clear once we discuss an example. So let me just discuss an example. If you have any doubt in any step, then you can anytime stop me, and we will discuss that thing again. So I'm discussing the same example as in the discussed in uh, the lecture notes. So F3, you all know that it's a field of 3 elements, right? And PT be the polynomial t raised to 8 minus 1 in F3T. So can you factorize t raised to 8 minus 1 in F3? Does it contain all roots in F3T? Anyone? So P of 1 is what? P of 1 is 1 minus 1, that is 0, right?
0
Yeah. So that implies that t minus 1 is a factor
of F3T.
of PT, right? And also P of minus 1 is what? This is again minus 1 raised to 8.
0.
Yes. This is 0, which implies that t plus 1 is also a factor of PT, right? But what else? So PT is definitely some t minus 1, t plus 1 times some, what to say, qt, such that qt belongs to F3T. But we have to factorize this qt also, right? So consider this polynomial again. So what we have, t8 minus 1. So this is t4 square minus 1 square. So we can use a square minus b square identity, and which gives that this is t4 minus 1 and this is t4 plus 1, right? Then again it's uh, t square and then minus 1 square. Again we can use the identity which gives us t square minus 1, t square plus 1 and t4 plus 1. Now t square minus 1, again the same thing, t minus 1, t plus 1, and then you have t square plus 1 and t4 plus 1. So these linear factors we are getting, no problem. We already got it from by just putting the values. But what about these two? Can they be linearly factorized in F3T?
I think no, sir. It is
Why?
first t square plus 1, whose factor will be in complex number.
Uh, okay, means it's just root of minus 1 is not a quadratic residue. Others were saying this. So simply, I will say that you have this is a degree 2 polynomial, right? So if t square plus 1 is reducible in F3T, then what are the possibilities for that it can have? Then t square plus 1 must be uh, a product of linear factors, right? Because it can be written as just if it is reducible, then one has to write it as two polynomials of lower degree, which means that in case of 2 degree 2, you just have the possibility that it has to be a product of two linear factors, right? And that means it has both the roots in F3 only. And thus, in F3, what are the possibilities? 0, 1, and minus 1, right? But none of 0, 1, or minus 1 is a root of t square plus 1 in F3 t, hence it is irreducible. So for degree 2 polynomial, it is very easy to check whether it's reducible or not. Okay, so hence t square plus 1 is reducible in F3T. You just put the values of the field. If it is satisfies the polynomial, then it is reducible, otherwise it's not. So that means we cannot linearly factorize this polynomial t8 minus 1 in F3T, but we have to linearly factorize it in some extension of it. So what we will do the same thing that we discussed earlier, that take the map, maybe the better word is define phi to be F3 from F3T to F3T modulo t square plus 1, the ideal generated by t square plus 1. So this is a irreducible polynomial, right? That we all know now. And it's an integral domain. It's in fact a principal ideal domain because uh, uh, that's F3 is a field, right? So it's a principal ideal domain, and this is a irreducible polynomial, means the ideal generated by this is an irreducible polynomial, and which implies that this ideal let's say this ideal is a maximal ideal. Maximal ideal. Oh, I should use some other color because it's already been used above. So it's a maximal ideal, right? And an integral domain modulo a maximal ideal means it's a field, right? This turns out to be a field. That trick we have used several number of times. Last time also we used. So this is a field. So the map from F3T. Uh, so, uh, so this is a field, and the map that we are defining here is T going to alpha. Okay. So by the same thing, P of alpha becomes 0 because P of alpha is nothing but uh, phi T of uh, mm, sorry, phi of pt, and that is 0 inside this, so it becomes 0. P of alpha is 0. So alpha p alpha equal to 0, that means that alpha is square plus 1 is 0, and it is inside this field f3t modulo t square plus 1. So we have adjoined the root alpha to f3, and then we have got this point field f3t modulo t square plus 1. So this field contains the root alpha, and yeah, so means it's a polynomial. So it's a it's an element of the field such that alpha is square equal to -1. So that's how the idea of iota comes into the picture. You just adjoin uh, a root of the polynomial t square plus 1 to the original field, and then this adjointment is will give you a new field that contains the alpha element. Okay, so alpha is a root such that alpha square minus 1 is, sorry, alpha square plus 1 is 0. So this is a new field which contains, and of course it's a field, so it contains 1 and -1 also. So it contains 1, -1 and alpha. So three roots we have got now. So this implies, so let me use the earlier color again. This implies your t square plus 1 is equal to t square uh, uh, minus 1 you can write, and this is t square minus alpha square. So this we can do in this new field. Say I am defining this field by maybe f1. Okay, so in f1 t we can do these calculations because this alpha lies inside f1, but it was not inside f3. Okay, so be aware of that. So now we have t square minus alpha square, so we can write it as t plus alpha and t minus alpha. So this polynomial also factorizes that as linear factors. Okay, now what? So uh, t square t4 plus 1 is still remaining, so we can write t4 plus 1 as again the same trick we will use, t4 minus -1, and that is t4 minus alpha square. Now again a square plus b square condition arises, so it is t square plus a square minus b square condition arises, so it is a plus b and a minus b, that is t square plus alpha and t square minus alpha. Okay, so yes, so now again this polynomial may or may not be reducible or irreducible in f1t. Yeah, so so we have to find an extension of f1 now such that it contains this the root of this polynomial as well. So how to do that? So let me just pick, let us pick t square minus alpha first. So what we want a element in some extension of this f1 such that its square becomes alpha. Okay, so uh, yes, 1 minus alpha square is alpha. That is correct, Adarsh. Thank you. So as Adarsh pointed out, 1 minus alpha square is what? 1 plus alpha square minus 2 alpha, which is nothing but 1 plus alpha square is 0, and that is uh, minus 2 alpha. And uh, uh, see, minus 2 is nothing but equal to 1 in f3 and f1. Why? Because f1 is just an extension of f3, right? So it will have the same characteristic as f3. Okay, so if you take an extension, the characteristic is not going to change if you are taking a finite extension, right? Because characteristic is what you add one n many times, and you will get zero after n steps. So that minimal n is called the characteristic. So in f3, if you add 1 3 times, that is 1 plus 1 plus 1, you will get 0. So the characteristic is 3. So in any extension also, because f3 is sitting inside that extension f1, so the characteristic won't change, right? So in f1 also the characteristic is 3, and that means minus 2 is same as 1. So this is nothing but alpha. So 1 minus alpha square equal to alpha. So this implies that 1 minus alpha satisfies t square minus alpha equal to 0. And similarly, you can check that alpha minus 1 also satisfies uh, t square minus alpha equal to 0. Okay. And they are different roots because minus 1 is not same as 1 here. We are not in f2. So 1 minus alpha is different from alpha minus 1, right? So they are different elements in f3. So these are two roots of t square minus alpha. Now you can check that 1 plus alpha square is 1 plus alpha square plus 2 alpha. So this part is 0 because alpha is equal square equal to minus 1. You have 2 alpha, and you are in characteristic 3 field. So this is minus of alpha, and this is happening because 2 is equal to minus 1 in f3, right? So this implies 1 plus alpha, and if you take the minus of it, minus 1 minus alpha satisfies t square plus alpha equal to 0, right? So now you can uh, linearly factorize pt. So pt is what? You have t minus 1, you have t plus 1, then you have 1 plus t square, right? 1 plus t square is this, t plus alpha, t minus alpha. This is t plus alpha and t minus alpha. So this is nothing but 1 plus t square, right? And then you have 1 plus t4. So 1 plus t4 is what? 1 plus t4 was t square plus alpha and t square minus alpha. And t square plus alpha was uh, t minus first root is 1 plus alpha, and second root is uh, minus 1 minus alpha, that is t plus 1 plus alpha. So this is what? This is t square plus alpha, right? And then you have t square, from t square minus alpha, you have to multiply by t minus 1 plus alpha and t minus, sorry, plus 1 minus alpha. So one root is 1 minus alpha and the other is alpha minus 1. Okay, so that's why this is nothing but you t square minus alpha. So that now you can see that this is a linear factorization of this polynomial, but we are in f1t, not in f1, not in f3. So here f1 means this extension, right? It's not just field of one elements. So maybe I should write some other notation because it's confusing. So what if I write uh, f3 dash maybe? So yeah, so it's some extension of f3 which contains all roots of this polynomial. So similarly for any field and for any extension for any polynomial inside it, we are sure to get a extension such that it contains all the roots of the given polynomial. Okay, so is it clear? So I think that's the
Uh,
whole. Yes,
Hello.
yes, Vivek.
Yes, sir. F3 that means 0, 1 and minus 1.
Yes, yes,
Always.
yes. F3 means just a field of three elements.
Okay. Then it will be an arbitrary field or
See,
always.
any field of three elements is isomorphic to each other. So
So we
that
can take it 0, 1, minus 1.
yes, and in the next lecture there is a theorem that for a given order, you have a unique field corresponding to that order. So for any and every field has order p raised to n. So
Okay.
not just for F3, for F9, F27 also there is a unique field of that particle of that order. Okay, so you can
Okay.
consider F3 without loss of generality to be 0, 1 and minus 1. That's it. Okay.
Okay. Okay.
Okay, so now lecture 3 we can start. That means the repeated roots, that is based on the repeated roots of a polynomial. Repeated roots. So what does this mean? So the lecture started by defining the derivation of a polynomial, or yeah, I should write the derivative of a polynomial ft belongs to the uh, ring f of t. Okay, so how to define it? So still limit and continuity may not be may not make sense in ft, but derivative one can define in the same spirit that we define on the real uh, numbers, functions on real values. Uh, so in the same spirit, we can define derivative of a polynomial with coefficients in any field. Okay, so this ft is generated by as a ring generated by 1 t square so on. Okay, so uh, what one has to do, so uh, this derivative is defined in that sense, define d, which is a function from ft to ft to be the linear transformation, not just the function, to be the linear transformation such that uh, d of tn is equal to n times t of n minus 1. And this is for all n greater than equal to 0. So once you define it on the basis, then as it's a linear transformation, the addition for on addition, it will also be defined, and for scalar multiplication, it is also defined. Thus, it is defined for any polynomial, because any polynomial is just a linear sum of these uh, uh, basis elements, right? So that's how the derivative of a polynomial is defined. So this is a linear transformation. So we have f plus minus g is equal to d of f plus minus d of g, and you can also check that d of fg is, it satisfies the Leibniz rules also, that f of d of g plus d of fg, and it happens for all fg belongs to. So that's how the derivation is defined. Now the another definition is uh, of repeated roots. So it says that if ft is a polynomial in capital F of t, then an element alpha belongs to an extension of f. So alpha may not be inside f, but if alpha belongs, even if alpha belongs to an extension of f, then it is called an repeated root if t minus alpha square divides f of t in e of t. Okay, so very similar to the same speed that we used to define the real valued functions, a repeated root of it, that if it has a quadratic uh, factor of alpha inside and some extension of et. So in the original field, maybe ft may be irreducible, but we have seen that there is just an extension where it is reducible as a linear factors, and thus, and in that extension we may consider the all the roots of it, and if it has a repeated root, then the power of t minus alpha must be dividing ft. Okay, so as an example, you can see T8 minus 1 belongs to Qt has no repeated roots. Why is it so? Can anyone just say quickly? Because we factorize it in linear polynomials, but uh, we didn't get a repeated root, right? We factorize it even in a smaller field, that is f3t. So how it was factorizing? It was factorizing like that. So it has no repeated root, right? You can see.
Yes, sir.
So yeah, so it serves as a counter example, while you can also uh, see another example, which is a positive example of it, that is mm, uh, t plus iota square and t minus iota square. If you expand it, then what it will be? This will be nothing but t4 plus 2t square plus 1. And this belongs to q of t, right? T plus iota, t minus iota, it will be just t square plus 1, right? So this is nothing but t square plus 1 whole square. So it is t4 plus 2t square plus 1. So this clearly has repeated roots, right? So in Qt, you can only reduce it as the square of the polynomial t square plus 1, right? So this is equal to t square plus 1 whole square in Qt, but you cannot further uh, re reduce it in Qt because it has no iota and minus iota, right? But if you take an extension of q, that is q adjoint iota, then you can factorize it in linear polynomials, and then you can see there are two linear factors corresponding to iota, and there are two linear factors corresponding to minus iota. So this polynomial has repeated roots. Okay, so now there is a theorem which gives the guarantee of repeated roots. The theorem says let uh, f be a field, f be any field, and ft belongs to the polynomial ring over that field, then this has no repeated roots if and only if the GCD of ft and derivative of ft is equal to 1 in ft. So we need not to go to an extension also just to say whether it has repeated roots or not. You just evaluate the derivative of this polynomial, and if they have a common factor, then there will be repeated roots, and if they have no common factor, then there won't be a repeated root. So it's an if and only condition. Okay, so yes, and then why it is useful, because it mm, it directly tells you that whether after going to an extension you will get repeated roots or not. Okay, so there is one more theorem which is important in this regard, discussed in the same lecture. So I will just state that. So ft has if ft belongs to ft is irreducible in ft, of course, then ft has repeated roots. So for irreducible polynomial, you have one more if and only if condition, that if it is irreducible, and then it has repeated roots if and only if the derivative of the function is 0. Function is 0. Okay, so yeah, that's uh, it from lecture 3. So let me just quickly say what is in lecture 4. So there was only one lemma that was discussed in lecture 4. So let me just quickly recall it. So 4 is on Gauss lemma. So what Gauss lemma says, Gauss's lemma. So it says if you can factorize something inside Qt, then you can also factorize it inside uh, Zt. So if Ft belongs to Zt and content of F is equal to 1. So this content I will explain. So content I will explain. So Ft belongs to Zt, content of F equal to 1, and you have, and Ft is equal to Ut times Vt in Qt, means you can factorize it inside Qt. Then there exist some rationals such that Ft is equal to A times Ut and B times Vt, where Aut and Bvt belongs to Z of t. So if you can factorize a polynomial in Qt, then you can also factorize a polynomial in Zt. So factorizing, see, if you can factorize it in Zt, then Z is contained in Q. So of course you can factorize it in Qt as well, right? But the converse thing is not straightforward. So this Gauss lemma says that the converse is also true, that if you can factorize it inside Q, then you can also factorize it inside Z. Okay. So for that, we need the definition of content. So let me just write what is a content. Content of F, that is denoted by C of F, right? So let F be the polynomial A naught plus A1 T plus so on to an Tn. Then the content is nothing but the GCD of A naught, A1, and so on to An. So just you take, calculate the GCD, and that is the content. So the content is multiplicative also. There is a lemma which is also being used in this proof, that for, and it's an important lemma. So let me write it. So if you have two polynomials in Zt, then content of U times content of V is equal to the contents of UV, right? Okay. So next it has a corollary, which I think one can skip because it's a direct application of it. So this lecture contains only Gauss lemma, it's its proof, and you should have this with you because it is very important lemma, and it gives an important criteria for checking irreducibility, that is called Eisenstein criteria, and the entire lecture 5th is on this Eisenstein criteria. So let me just write the theorem. So it says let Ft is equal to A naught plus A1 T plus dot An Tn belongs to Z of T, such that there exists a uh, prime P satisfying this. First, P uh, does not divides An, the leading coefficient. Second is P does not divides A naught, A1, so on to An minus 1, all other coefficients. Sorry. It is P divides A naught. So it does not divide the leading coefficients, but it divides all other coefficients, and it should not divide, the square of it should not divide A naught. Okay. If these three condition is true, then Ft is irreducible in Z of T. Okay. And if it is irreducible in Z of T by Gauss lemma, this implies Ft is irreducible in Q of T, because Gauss lemma says that irreducibility in Qt is same as irreducibility in Zt. So you can also say that as a direct outcome of Gaussian criteria, it is enough to show that this is Ft is irreducible in Zt, and that you can do using Eisenstein criteria. Okay. So it has a wide application in this domain because it gives you a sufficient condition to check that whether a polynomial is irreducible or not in ZT or QT. So, for example, we can consider this polynomial t4 plus 18 t square plus uh, 30t plus uh, we have to do 375, right? So uh, can you quickly tell that whether it is irreducible using this criteria? So I will say yes, this is irreducible in QT. Why? Because take P to be 3, then 3 does not divides an, that is equal to 1, right? 3 divides 18, 30 and 75, and 3 square, that is 9, does not divides a naught, which is 75, right? Oh, I made a mistake here. Here it should be divide. 3 divides, right? So this
Okay,
is,
right.
so this implies that mm, ft is equal to t4 plus 18t square plus 30t plus 75 is irreducible in QT. So it gives a wide range of irreducible polynomials in QT. Okay. Okay. So it has a very interesting uh, application, you can say. So, and which I will state as a lemma. If P is a prime, then uh, 1 plus t square plus so on t raised to p minus 1 is irreducible in QT. So the first question that should come to your mind, that if we are going to use Isestian criteria, then how we are going to apply it, because all these coefficients have are so it has all coefficients to be 1. So what prime will divide this, right? But uh, we can make use a small trick to actually use Isestian criteria here. The trick. So see, if t if p of t is irreducible, then for any a belongs to f of t in general, f of t, let's say uh, p t of p t plus a is irreducible. And in fact, we can write it as a if and only if condition. P is reducible if and only if for any a in it should be f. F p t of a is irreducible in f of t. And it's a very straightforward thing to observe. Why? Because if say p of t is some p1 t P2t and dot dot to some say PR of t, it has some R many factors. Then what P of t plus a will have? P of t plus a will have the factors as t plus a, P2 t plus a, and dot 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 PR t plus a. So this is also a polynomial in FT, right? Because you just need to put a in terms of t, and then evaluating will give you a polynomial in FT. So if PT can be written as a product of R many factors, then PT plus A can also be written as R many factors. And the converse is also true. Converse is also true, right? Because if you can write PT plus A as P1T, P2T, PRT, then PT will be written as P1T minus A, P2T minus A, and so on. Okay. So the converse is also true. That means if PT is irreducible, if and only if PT plus A is reducible for any A. So now consider, so let's say I name it to be some g of t. So consider g of 1 plus t. So what it will be? So checking whether gt is irreducible is same as checking whether 1 plus g 1 of 1 plus t is irreducible, right? So you replace 1 plus t, sorry, t by 1 plus t here. So 1 plus t plus 1 plus t square plus so on to 1 plus t minus 1. Okay, this becomes this. Okay, so one trick is, since g of t is 1 plus t plus dot 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 tp minus 1, so it is same as t p minus 1 divided by e raised to p minus 1 divided by t minus 1. Why? Because you can see uh, uh, t p minus 1 is same as t minus 1 1 plus t. You can just uh, take the product and then see that this is equal to this. So
Sir, here you can say it is also a GP series like.
yes, see, that is okay, but you cannot use GP series for polynomials. Means it looks like a GP series, but in GP series you have constant multiples, right? Here t is a variable, so better to treat it as a polynomial.
Okay, sir.
Okay, so you can do the polynomial multiplication and then see that every other term will cancel out except the pth power term and minus 1. Okay, so that's why this, after multiplication of these two polynomials, you will get tp minus 1, and thus this is equal to this. So g of 1 plus t becomes, you just replace 1 plus t here, so this will be 1 plus t p minus 1, and here you have t plus 1 minus 1 minus 1 to minus 1 cancel out, you have to divide t only. So what is now, as an expect as an using binomial expansion, what you will get, 1 plus t plus pc plus not t, this will be 1 plus pc1, something like that, na? So 1 plus pc1 t plus pc2 t square, and so on to the last term will you that you will get is t of p minus 1 divided by t, right? So this minus 1 will be cancelled out with this. So you will have pc1t plus C2 T square, so on to uh, P C P minus 1 T P minus 1, and then at the end you have T of P, right? Now this point becomes a polynomial. So, and what is PCN? PCN is nothing but P factorial divided by P minus N factorial, N factorial. So you can check that P divides PC1, PC2, and so on to P minus 1. And since PC1 is equal to P factorial divided by P minus 1 factorial and 1 factorial and 1 factorial. So this is what P times P minus 1 factorial will get cancelled out, and this is just P. So, and of course, P square does not divides A naught, which is P, right? Oh, sorry. So P divides all coefficients, and of course, P does not divides AN, which is 1, and P divides all other coefficients, but its square does not divide A naught. So this means G of 1 plus T is irreducible using Eisenstein criteria. Eisenstein criteria. And hence G of T is irreducible using that G of 1 plus T is reducible. Okay. Okay. So that's why even if in the first tense it might look that we cannot use the Eisenstein criteria, but after doing some uh, manipulation, we will get that actually the Eisenstein criteria is applicable, and thus the polynomial is reducible. So as a consequence of it, we get that uh, in last lectures we observed that if zeta p is the primitive root, that is the root that generates all other roots, primitive root of uh, x p minus 1, then uh, since xp minus 1 is, as we say, saw above, that this is nothing but x minus 1, 1 plus x plus so on to xp minus 1, and uh, 1 cannot be the primitive root because any power of 1 will again be 1, so it won't generate and all other roots. So therefore zeta p satisfies must satisfies the other polynomial, that is 1 plus x plus x p minus 1, right? And by the previous lemma, we just came to know that this polynomial is irreducible. Of course, here I am considering p to be a prime, right? So this is irreducible in
Yes, sir. Okay.
Q of t, right? So this implies that if you adjoint uh, zeta p to q, then the degree of field
Minus
extension
1.
is p minus 1, right?
Okay, sir.
Okay. And As another corollary, we get if P is a prime and zeta P is constructible, then P minus 1 has to be uh, some power of 2. Why is it so? Because since it is a constructible number, so its extension, so q of zeta p over q, that is p minus v, must be some power of 2, and thus p minus 1 should be a power of 2. So, and in fact, it's a if and only if condition, because if it is not of power of 2, then you cannot construct it also, right? So it's an if and only if condition, that if P is a prime, such that zeta P so P is a prime such that zeta P is constructible if and only if P minus 1 is some power of 2. Okay, so that is something. Now, using the same idea, using the similar idea, uh, one can check that uh, zeta of Pm, where m is some natural number. So zeta of Pm means it satisfies, it's a Pmth root of unity, right? So we have x p raised to m minus 1. So it's a root of, so let me just write, that is the primitive root of primitive root of x raised to Pm minus 1, this polynomial, that is the primitive root of this, satisfies. Okay, let me, I just want to give a notation because it would be easier for me then. This polynomial we will denote, uh, right? So, yes, there to like give notation. Maybe I can just use this function and add some space. Okay, it's not possible. So I have to erase it and then define a notation, and then only I can proceed ahead. So let this phi uh, p of t is this polynomial 1 plus t plus dot dot tp minus 1. Okay, so using the same idea, in this using similar idea, uh, one can show that uh, zeta of Pm, that is the primitive root of xpm minus 1, satisfies phi P, and instead of T, you just replace it by T of Pm minus 1. P raised to M minus 1. P raised to Pm minus 1. Okay? Yeah. So, so what does this mean? You just replace this uh, T with Pm minus 1, P raised to Pm minus 1, and the polynomial, whatever you get, so it satisfies that polynomial, and check that this is also irreducible. This is also irreducible over Qt, right? So this implies that Q of any power, any pair power also now you have that zeta yes. So let me just see if there is anything I need to explain more. It's fine. It's fine. It's fine. Okay. Yeah. So this is P raised to uh, M minus 1. You have minus 1 here in the power. So this is also irreducible, and it has degree. It has degree. So what term will give you the degree of this polynomial? So when you replace t by p raised to m minus 1 in this last term, then this will be the highest degree term in this polynomial, and this will be of degree p raised to m minus 1, and then p minus 1 will also come from here. So p raised to m minus 1, p minus 1. It has degree this. And thus this implies that uh, q of zeta p raised to m over q has degree p raised to m minus 1, p minus 1. Okay. So that's it for uh, lecture 4. And maybe we can move to lecture 5. If any one of you has any doubt, then you can ask. Otherwise, we will quickly wind up these notes and then solve some questions. So lecture 5 is for existence of uh, finite fields. So it's called the existence theorem for finite fields. I will just write down the important results and then move to the next part. So maybe I can simply just state the main theorem. I don't think anything else is that much useful. So theorem says that let P be uh, any prime, then and n greater than equal to 1, then there exists a field of there exists a field f of order p raised to n. Right, and the converse is also true. That is, every finite field as order p raised to n for some prime p and n belongs to n. So whatever finite field you consider, it is always of the order p raised to n, and for each p raised to p, for each prime p and each n, you will always get a finite field. Okay. Okay. So mm, that's it. And then lecture 6, one can move, and it says that it is about the subfields of a finite field. So this is important because what kind of fields you can have. Uh, okay. So see, let E be a field of size p raised to n, and uh, if f is contained inside E is a subfield, then what you have, mm, then E is going to be E is a vector space over F, right? Because F is a smaller field, E is a larger field, so E is going to be a vector space over F, and it's a finite dimensional vector space. E is a uh, finite dimensional vector space over F. Okay, then let uh, the dimension of uh, E over F is say M. Then you can check that order of E is nothing but order of F raised to M. Why? Because E is a finite dimensional vector space over F. Now each element of E can be written as a linear sum of m many basis elements. And what are the possibilities? Say let's say let say basis of E over F is some uh, E1, E2, and dot 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 EM. Okay, then any alpha belongs to E uh, has the form alpha is equal to some A1 E1 plus A2 E2 and so on to AM EM, where AI belongs to the field F, right? So there are F many mod of F many possibilities for these AIs, right? So there are uh, mod of F many possibilities of each AI. And since they are the basis, so for one possibility of AI, you will get mod of F possibilities for others, right? And they are like non-interacting because they are the basis, so they are linearly independent. So, of each ai, and thus mod of e is nothing but mod of f raised to m, because there are m many basis elements. So uh, you have this, right? And what does this imply? Of course, as it is a field, so yeah, this imply that um, if mod of f is some p raised to r, it has to be of the form p raised to r because it's a subfield of mod of f, mod of e. So its cardinality must divide the cardinality of e, and this is because it's a subgroup, also is a subgroup of e under addition, and you can use the Lagrange theorem and then say that its order should divide the order of e, and it has to be some p raised to r uh, for some uh, r uh, for such that 0 less than equal to, of course, 0 greater than equal to r, less than equal to um, what we were using for e, yes, n. Okay. uh, and then mod of e is p raised to n, and mod of f is p raised to r, and this is m. So what does this implies? This implies r uh, divides r divides. Okay. So uh, if this implies that if f is a subfield of e, f such that mod of f is equal to p raised to r is a subfield of e, then uh, r must be dividing n. Okay. And this is if and only if statement, because for each p raised to r you are supposed to get a field, and you can also show that this field you can for each you can choose that field to be a subfield of e. Okay. So this is also an if and only if statement, that for each r dividing n you will get a subfield of e of order p raised to r. Okay. And the converse is also true. Okay. Yes. Now there is one uh, straightforward observation, that let f is contained inside E, and order of f is say p raised to r, then order of f star, which is nothing but you subtract 0 from f, this is going to be p raised to r minus 1. So uh, so this is a cyclic group that we will see in the coming lectures, but it has order of the field is f star, and it forms a group under multiplication. Okay. So this forms a uh, group under multiplication, right? Under multiplication. So what does this gives? This gives that any alpha belongs to f star satisfies this alpha of p raised to r uh, minus 1 equal to 1. So because it's an order of the f star group, so for any g belongs to g, g raised to order of g is equal to identity of the g, right? So alpha of pm minus 1 equal to 1, and this implies that alpha is a root of t raised to p r minus 1 equal to 1, and hence it is a root of is is a root of t raised to p r minus t. So it's a polynomial, so we should write it as a polynomial. So it is t raised to pr minus 1. So you are just multiplying t both side, right? So it's if you take t common, then it's just t raised to pr minus 1 minus 1. So it satisfies this polynomial, means it satisfies a polynomial which contains this factor, right? So it satisfies this also. Let me just put my charger on. So that's something that you should keep with you, because it's going to be useful in the upcoming th things. Okay, now here comes an important theorem which says uh, if order of E is equal to P raised to n, uh, then E has a unique subfield of order P raised to m, where for every uh, m dividing n. Okay, so we are not going to prove it, but the interesting thing would be to see the tower of field that will make your understanding better. So uh, say you have this last number 262144, which is f raised to 2 raised to 18, I guess. This is some power of 2, and this is some other power of 2, and this is some other power. So what this power is? This is 2 raised to 1024, and then this is 2 raised to 12. Okay, and then this is 2 raised to 18, perhaps. I guess 2 raised to 18. 8, then 16. Yeah, 2 raised to 18 it should be. And then 256 you have here. So what power is this? This is 2 raised to 8. This is 2 raised to 8. So by this theorem, if we consider f raised to uh, f16, which is 2 raised to 4. So can you tell which of the fields which have this field as a subfield? Anyone? So can it be a subfield of 2 raised to 12? 4 is dividing 12, right? So it will be a subfield of this. And 4 is also dividing 8, so this will also be a subfield of this. What about 2 raised to 18? Factors of 0. I couldn't understand this, what you want to say. Factors of 18. Okay. So this won't be a subfield of this. But if you consider f raised to 64, which is 2 raised to 6, then it will be a subfield of this, and this will also be a subfield of this, but this won't be a subfield of 2 raised to 8. And if you consider f raised to a field of cardinality f2, f12, that is 2 raised to 9, then this will contain be contained in this. Okay, then you can have something else bigger number also, and here also you can have some bigger number which contain bigger field will contain these fields. And f raised to f16 will contain uh, f4 for sure, because f4 is nothing but 2 square, 2 divides 4, and then this 2 also divides 6, so it will also be contained in 2 raised to 6, but it won't be contained in 2 raised to 9. And if you consider f raised to 8, f8, sorry, that is 2 cube, then this will be contained in this, and this will be contained in 2 6, that is this, and then f2, that is 2 raised to 1, this is will be contained in this, and this will be contained in this. So this is a tower of fields, you can say. And so if you ask what are the fields, subfields of 2 raised to 18, subfields of 2 raised to 18, that is, oh sorry, subfields of f2 raised to 18, that is a very big number, 2 6 2 1 4 4. Then by the previous theorem, you need not to worry about this last number. You just need to find the divisors of the smaller number 18, and that tells you that these are nothing but f2, f6, sorry, f8, f so f2, f8, f4, and f raised to 64. 4, f64, and also this f12, f512. It corresponds to divisor 1. It corresponds to 3, it corresponds to 2, it corresponds to 6, and it corresponds to 9. Okay, so this is looking like 218. This is 2 raised to 18. So divisors of 18 are 1, 2, 3, 6, and 18. And of course, it contains itself as a subfield also. Okay, yeah. So that's it in this lecture. Uh, so the next lecture contains uh, the results on multiplicative, multiplicative group of a finite field. So what it is? It is, oh, yeah. So this first theorem says that if F is a field, F is a field, then F star, that is F minus group. Okay, and any finite subgroup of F star, that is F minus 0, is cyclic. Okay, so here F need not be a finite field. It's just any arbitrary field, and for any arbitrary field, if the any finite subgroup of F star is cyclic. So here by subgroup I mean the subgroup with respect to multiplication. Okay, multiplication, right? Should write it more because F star forms a subgroup under multiplication. So any subgroup of it as a multiplicative subgroup, it must be cyclic. And in particular, F star is cyclic. Okay. Okay. Then uh, that's the only thing I found important to be discussed in this lecture. So the next theorem is as Vivek, I guess, he asked, can I about the uniqueness part some times before. So uh, this theorem gives you the uniqueness. So this is uniqueness theorem for finite fields. So just a single statement I will state uh, for this lecture. So this says that uh, let E and E prime are finite fields of order e raised to n, then there exists an isomorphism of field extensions. It's not just an isomorphism of fields, it's an isomorphism of field extensions, which is something uh, even a better statement that it preserves the base field. Yeah. Isomorphism of field extensions. E to E prime, keeping the base field Fp to be fixed. That's why I told that there is only one field of order p raised to n because all fields of p order p raised to n are isomorphic. Okay. Okay. So uh, now it's time to okay. So it's time to discuss some solved problems. Okay. I can tell some sample problems so that you can solve assignments. I won't be discussing more because there is very less time left. But I can tell you something um, so that it uh, gives you a better understanding of the things. So first question you can take this color. This I can use. How many irreducible how many automorphisms we can construct of a field? So it is not an easy problem, I guess, because uh, in general, to even see that whether two fields are isomorphic or not, that's also as discussed in the first week notes. That's just not an easy problem, but mm, what this theorem says that there will always be an field uh, isomorphism of field extensions. So that gives you uniqueness of the field, but for a given field, uh, I think it's bit challenging. It's not that much straightforward, but there should be a theory of for that because finite fields have been explored very nicely. So I'm sure that there should be some theory of it, but that's of course beyond this course at, as it seems to me at least. Maybe you can try with the base fields. For base fields, it's going to be easy, I guess, because you can try with Z mod PZ. There it should be easy, but as you go to the higher extensions, then the problem becomes difficult. For base field, you can easily see. You can just map generators to generators, and I think that will work. As a field automorphism also that will work, it seems, maybe, or there might be some issue. You see, means for base field, it's going to be easy, that I am sure. But as you go the higher extensions, then it might be difficult. Okay, so let's come back to this question. So the question is, how many monic irreducible monic irreducible polynomial of degree 2 are there in FPT? Okay, so one has to see how many degree 2 polynomials that are reducible and monic are there. So that's a counting problem. So how many polynomials are there for monic polynomial? So a monic polynomial of degree 2 in FPT is of course of the form ax square plus, oh sorry, the leading term should be 1, so it is of the form x square plus bx plus c, such that uh, b and c belongs to FP, right? So this implies there are p square uh, monic polynomials, distinct monic polynomials in FPT, right? And out of that, uh, yes, p square, you are right, Vivek. So out of it, we have to find the polynomials which are also reducible, and then from these p square we can divide the minus, subtract the reducible ones, and then we will get, right? So these are the total number of polynomials. Now how to see the reducible polynomials? See, again we will use the same trick as we used before, that it's a degree 2 polynomial. Degree 2 polynomial is reducible if and only if it factors into linear polynomials, because the only possibility of it factors are just linear polynomials, right? So let's count the reducible polynomials, right? So reducible polynomial is that implies if PT belongs to FT is FPT is reducible, then there exists alpha and beta. There exists alpha and beta uh, belongs to FP, such that uh, PT is equal to T minus alpha and T minus beta, right? So uh, so how many irreducible polynomials are there? reducible polynomials are there. This implies number of reducible polynomials is just you have number of uh, choices of, of alpha beta, this pair, where repeated alpha may or may not be equal to may or may not be equal to beta, and that is because we are choosing it from FP, so this has to be from P plus 1 2, or one may write it as P plus 1 C2. Why? Because if you want to choose n many objects from a set of m objects and with repetition allowed, then the possibility then the choices are m plus n minus 1 n. Okay, if you want to choose m many objects from a set of n objects, then the with repetition allowed, then it is m plus n minus 1 choose n. If repetition is not allowed, then you'd have just m choose n. But since the repetition is allowed, so then m plus n minus 1 choose n. And here m is 2, so it is nothing but, and n is p, so it is nothing but p plus 2 minus 1 by choose 2, that is p plus 1 choose 2. So this is the uh, reducible polynomials, and this implies number of irreducible polynomials are number of irreducible polynomials is equal to p square minus p plus 1 c2, and p plus 1 c2 is nothing but uh, p plus 1 factorial divided by 2 factorial, and then p plus 1 minus 2, that is p minus 1 factorial. So you can see this is nothing but uh, p square minus p by 2. Okay, and let's denote it. Let's denote it by the uh, symbol phi 2 of p. Okay, in general, phi d of d will denote uh, the number of irreducible polynomial of degree d. So, okay, now consider the same question, but for higher degree. How many uh, monic irreducible polynomial of degree 3 are there in Fp of p? So here the situation becomes a bit tricky, because now even if you don't have the factorization as linear factors, still it may be reducible. Why? Because uh, if okay, let me first uh, say something. So total monic polynomials in FPT is by the same argument is of p cube, because it's monic, so it has to be of the form x square plus ax plus b plus c, right? A, b, c are in FP, so it has to be, there are p cube many choices, so you can think like that. So there are p cube monic polynomials, and then we again by the same trick we use we will first calculate the reducible polynomials, and then uh, we will be subtracting it from the total number of polynomials. Okay. So these are the total number of polynomials in P cube. Then it contains phi 3p. Okay. That is irreducible monic polynomial of degree 3. So it is same, like if you say irreducible monic or monic irreducible, it's just nothing. So irreducible monic polynomials of degree 3, it's just the cardinality of that. Okay. Plus you may have your polynomial to be a degree 2 polynomial, irreducible polynomial, and a linear polynomial, right? So this is the cardinality. This corresponds to the number f2, or maybe some ft times gt, where it is irreducible monic of degree 2. Okay. So this f is irreducible of degree 2 and gt is a linear factor. It's nothing but a linear factor. So it's just f1p, right? Now the second thing you can have is uh, three linear factors, polynomials having three linear factors. Okay, so these are the only possibilities. You have irreducible polynomials of degree 3. You have uh, polynomials, irreducible polynomials of degree 2 times the polynomials of degree 1. And you have three polynomials having linear factors, right? So now, uh, uh, let's see this in more detail. This is a polynomial of the form x minus alpha, x minus beta, and x minus gamma with repetition allowed, right? With repetition allowed. So by the same trick we use above, that the number of selections of n number of selection of m many objects from a set of n many objects with repetition allowed is m plus n minus 1 choose n, right? So this has cardinality. M is 3 here. So n plus 3 minus 1 n choose n, that is, this should be choose n. So that is n plus 2 choose n, right? That I will write here. So here n is fp. So sorry, n is phi 1 of p, the linear factors. These of course your this is phi 1 of p choose 2, and this is uh, 3, right? Because you have to choose n many objects. So the formula was n plus m minus 1 choose m, right? So m is 3 here and n is f phi 1 of p. Now what is phi 1 of p? Linear factors, irreducible linear factor is alpha can, so x minus alpha, alpha is varying over fp, right? So this phi 1 of p is nothing but p, right? So this is p plus 2, 3. So that means you have, which implies you have p cube to be phi 3 of p. Oh, I made a very silly mistake. So I denoted it by xi for a particular for a reason that I don't want to confuse you guys with the uh, Euler phi function. But I'm again using the same notation. So let me just quickly change the notation. This is xi2 and this is xi1 and this is xi3 of p plus uh, xi2 of p, xi1 of p, uh, we know here, so also it should be xi1. One has to be careful about the notations. This is xi1 of p. Okay. Okay, so xi1 p, we know that this is p plus this number is p choose 2, p plus 2 choose 3, right? So uh, this is p, this implies that phi 3 of p is pq uh, minus xi2p. We calculated it was p minus p square minus p by 2, and we have p also, so p times p square minus p by 2, that is for this. And this is p plus 2 choose 3, which is nothing but p plus 2 factorial divided by 3 factorial, and p plus 2 minus 3, that is p minus 1 factorial. So when you solve it, you will get that this is pq minus p by 3. Okay, so here you are getting p square minus p by 2, and here you are having p cube minus 3. So try to see if in general the number of irreducible polynomials over fp is p raised to d of degree d is p raised to d minus p divided by d. So it's an exercise for you guys, and uh, I will just uh, show one thing, because that is an important uh, thing that I should discuss, and then I will stop. So I was supposed to discuss one more question, and yeah, means I think I can discuss. So that's an easy question. So prove that t raised to t cube plus 48t minus 24 is irreducible in qt, and that's an straightforward check, because uh, can you just say why it is? Yeah, not t equal to 3. You need to take p equal to 3 and apply Eisenstein criteria. Eisenstein criteria. Okay. Okay. Now, so the converse of Eisenstein criteria may not be true. Means if some polynomial is irreducible, it's not necessary that it will satisfy the Eisenstein criteria. Or if the Eisenstein criteria is not satisfied, it doesn't mean that the polynomial is reducible. So for that, one question I wanted to discuss, that is uh, x4 plus 4 is uh, irreducible, is x4 plus 4 is irreducible in qx. Okay, so you can see that Eisenstein criteria is not satisfied, because the only choice of prime that you can take is 4. So, but no, Vivek, it is not satisfied, and that's what I'm going to tell. It's not satisfied. So the only choice of prime that you can take is p equal to 2, but Eisenstein, so p equal to 2 is dividing a naught, very good, and p equal for p equal to 2, and p is not dividing a1 a2, that is till Sorry. I'm doing very silly mistakes. So you can take p equal to 2, and p is not dividing an, that is 1, and of course p is dividing a naught, that is 2, and a1, that is 0, and so on to uh, an minus 1, that is also 0. But the other condition, that is p square does not divide a naught, that is 4, this is not satisfies, because 4 is divisible by p square, that is 4 itself. So Einstein criteria is not satisfied, but still the polynomial is irreducible. That's what the main goal of this example, and how one can show that it is irreducible. So see, x square plus 4 is always greater than equal to 0 for any x belongs to real numbers, right? In particular for rational numbers. So this implies x square plus 4 has no real roots. In particular, it has no rational roots. It has no rational roots. So that means if it is reducible, that means if x square 4 is reducible, then it has to be of of the form a x square plus ax plus b, and uh, x square plus cx plus d, right? Because it cannot be factorized as linear polynomial. It has to be a product of two polynomials of degree 2, right? Because it has no roots. And then also, if you compare it, this implies b power 4. Oh, yes, power 4 is missing. Yes, x4. Okay. Yes, x4 plus 4. From here, the power 4 is missing. Thanks, uh, Vivek. So it's 4, 4, 4, 4. So if you simply multiply it, you will get that BD should be equal to 4, right? Because BD will give you the constant term, and then it has to be equal to 4. And this implies that, so let's try with B equal to D equal to 2. And that is x square plus, sorry, again the same mistake, x4 plus 4 is x square plus ax plus 2, and x square plus cx plus 2, and this is x square plus a plus b x cube 4 plus 4 plus ab x square plus 2 times a plus b x plus 4, and just a second. So this implies your a plus b has to be 0 because it is the coefficient of x cube, and 4 plus ab has to be 0, and this implies that a equal to 2 and b equal to -2. So you are getting a choice for which it holds. This implies that x square plus 4 is reducible, and it is x square plus 2x plus 2, x square plus, sorry, very very silly mistakes I am doing. So I should put a c wherever b is there, because it's, let me just write it again. C 4 plus ac x square, and then 2 plus a plus cx. So a plus uh, c is equal to 0, and 4 plus ac is equal to 0. C is equal to 0 and 4 plus AC is equal to 0, and then B is C is equal to -2, is equal to -2. So this is -2 x plus 2. So it is irreducible. It is reducible. So Isistine criteria is not satisfied, but we are getting the polynomial to be reducible. So it somehow tells that so it's actually a positive example for the converse to hold, but actually it won't hold in general. So I took it as an example to show you that it won't be it will tell you that isistine criteria is not true in general, but it supports the converse to be true, that if it is reducible, isistine criteria is not satisfied, then the polynomial is reducible. But in general, even if the criteria is not satisfied, you can get the polynomial to be irreducible. So you can still take it as an example to show that x square plus 4 is reducible in qx, because it does not use isistine criteria. The converse is not true in general, but you can use this kind of tricks to show that whether a polynomial of degree 4 is reducible or not. So you can first see that if whether it has linear factors, and if it has linear factor, then it is reducible, and if it is not having linear factors, then try to expand it as a uh, product of two quadratic polynomials. Okay, so yeah, that's it. I hope it's clear. If any doubt or question, then you can ask. Otherwise, we will stop here. Okay. Uh, okay. Thank you, Vivek. So if there is no doubt, so let me stop sharing. So one announcement that I want to make is so the next class is supposed to be on 13, right? So mm, on 13 I may not be available, so I will request the NPTEL team to uh, postpone the session to most probably to 15 on the same timings. So you will get a mail regarding that. And yes, so most likely we will meet next on the 15th, that is the Thursday of next week, on the same time, 6 to 8. Okay. Okay, then I will end the meeting here. Thanks.